Hello, this presentation is about hydrogels. Hydrogels are interesting molecules which can hold water, and their obvious use is in soil where they can retain water, and this presentation will tell some of the aspects of its use, different uses. Now, the World Food Challenge is one of the things which makes this particular topic very important. We have a growing population, we have droughts, we have topsoil erosion. Obviously, we need to find out some way by which we can retain water. Now, one thing I should caution is that other than soil, there are other aspects where we find use of hydrogels. For example, they are used in disease handling, for example, in different hydrogel nanoforms. They are used for release of drugs, and other than soil and sensors are also very interesting things. What they do is they somehow conjugate hydrogels with some kind of sensing device to make very interesting sensors. Pressure sensor is one of the obvious things which is used, and now how they actually do their task of containing water is they are hydrophilic cross-linked polymers, and they are super absorbent. And one of the goals in particularly agriculture is to grow food with less water. Now there are issues. For example, it is toxic, it is expensive, and it has short life. Toxicity has been handled because there are new formulations, polymeric formulations of hydrogels, which is making it less toxic, and it is now not so expensive, and its short life is actually good because that makes it biodegradable. So all these three issues have been handled. Now, other than the mentioned uses, they are used in sanitary napkins and drug delivery agents, cosmetic industries, and they are used as tunable pressure sensors, which I have already mentioned. Now, this actually has made its way to the EPA approval. Hydrogels are now EPA approved, and we know that any agent which is used in environment and soil has to have this EPA approval. And there are some real-time data. Broccoli has seen 35% more yield with 25% less water. Similar data is available with lettuce and tomato. Now, typical requirement is 10 kg per acre, so one can find out the economics of hydrogel use. This is how it looks like in the molecular level. The dry hydrogel is in the left panel and swelled hydrogel is in the right panel, and see how it traps water inside those cages and retain its evaporation. This is one picturesque illustration of what really happens. You can see in the left panel rainwater is falling and there is a growth of plant, but in the right panel the hydrogels make it grow without such rainwater. This is another microscopic image of this swelling process, how water droplet surrounds it and it actually soaks the water, and so ultimately it has come to some saturation level at some stage from A to F. This is a typical model showing how the water uptake occurs. T is time, W is the water mass, and A and B are constants. And this particular simplified model actually is related to this particular differential equation, where you have the rate of change is varying with W infinity minus W square, where W infinity is the water uptake at very large time, long time. And you can see the typical saturation kinetics behavior of water uptake using this model. Now, we can modify this model by using a Langevin term. For example, RT is a white noise whose autocorrelation is the delta function. Now, there is also a power law model where at time t and time infinity, the rate is the water uptake is expressed by a power law k t to the power n. Now, the significance of n is important. If n is equal to 0.5, the water transport is controlled exclusively by the chemical potential gradient, which is also called the Fickian diffusion. If n is equal to 1, the rate of volume variations of the hydrogels is proportional to time t. And in real life, it can vary between 0.5 to 1 depending on what kind of water flow is actually occurring. Now, the plan which we have in mind is that this exponent itself is a function of time. So, NT profile will give us a time series, and we can see here that typically this is the fixed diffusion model in its simplified form, which would lead to this second order non-uniform type of diffusion equations, where you have a gradient term, and in the left side is a rate term and the right side is a double gradient and single gradient terms. And if we integrate this, we will get a simplified relation between MT and infinity, and the A and B in this case will be given by some expansion of a polynomial which can be numerically solved. Now, in this equation, the phi f and phi r are the contributions from the fixed diffusion and the chain relaxation by the hydrogel. If we are able to detect the kinetics of water flow via IoT, we may find out the optimal values of phi f and phi r that would produce the desired results. Obviously, feeding the time series IoT data to the stated diffusion models may be a challenging task. So, that is all for now, and this is how it looks like. The diffusion in the background. The real thing is diffusing. Basically, hydrogel is all about diffusion. Normal diffusion by following Fick's law, and diffusion through a polymeric matrix. And how it varies with time is the question, and if we can use IoT using standard sensing devices, IoT based sensing devices, that can give us very interesting informations. Lastly, thank you very much. I hope you enjoy this presentation.